Hi, I am architect Archana Agarwal. This video is on sustainable building materials and life cycle assessment. It is based on GRIHA version 2019. The world that we are living in is transforming at a very rapid pace due to the increasing population and its shift towards urban areas. As per the UN Department of Economic and Social Affairs, it is predicted that by 2050, around 68% of the world population will migrate to urban areas. From the graph on the screen, it can be observed that in 1960, the population in rural areas was twice as high compared to the urban areas, but it equated in 2007. However, by 2016, the urban population increased to 4 billion, while the global rural population increased to 3.4 billion, reflecting an increase in the urban population over the rural population. An overall growth in the global population directly calls for the need to provide affordable housing, transportation, utility infrastructure, and related services, bringing tremendous stress on the materials and resources. The challenge lies in delivering the requirements at an affordable cost with the least impact on the environment. In India, by 2016, 33% of the population was residing in urban areas, as can be seen in this figure. The effect of urbanization is most profound in Tier 1 cities, where a large influx of migrant population is causing housing demand to surge. Moreover, rising income levels and the transformation of the Indian population from the lower middle class to the upper middle class, as seen in the figure, has affected consumer behavior. It has empowered an increasing number of people to live independently, which has subsequently led to increase in individual resource consumption. The last 30 years has witnessed a sudden and substantial growth in material demand, specifically for metal ores, thereby increasing the rate of extraction of metals. The graph on the screen shows that the demand for construction minerals has also extended rapidly. And the outcome of this growing consumption of material resources is that the amount of solid waste generated by economic activity is also rising. The projections are that 1/5 of the raw material extracted worldwide will end up as waste. The Global Status Report 2017 by International Energy Agency indicates that the floor area additions, especially in developing countries like India, are anticipated to be nearly 20 billion square meters over the next 2 decades, as seen in the figure. Increase in the floor area implies increased demand for construction materials. India's per capita material consumption is lower than the rest of the world, as can be seen in the graph on the screen. However, the large population ensures that when depicted in absolute terms, India's resource consumption was as high as 8 billion tons in 2020, as seen in this figure. A study was conducted in 2013 by IGEP, that is Indo-German Environment Partnership Program, which is a joint program of the Ministry of Environment and Forest, Government of India, and the Federal Ministry for Economic Cooperation and Development. According to this study, the continuation of the current population growth and economic trends will result in India's material requirements, especially fossil fuel and non-metallic minerals, to be almost 15 billion ton by 2030 and near 26 billion tons by 2050. In such a scenario, meeting India's resource demand will be a challenge. The report of 2017 by International Energy Agency states that 11% of the total global energy-related CO2 emissions are attributed to the construction industry. In India, reinforced cement concrete, that is RCC, is the most prevalent material used in the construction of conventional buildings. RCC is an energy-intensive composite material that consists of steel reinforcement bars in concrete. This relays into cement and steel, becoming the most sought-after materials in contemporary construction practice in the country. India is the second largest cement producer in the world. A total consumption of about 270 metric ton was the annual trend since 2016, which rose sharply in 2019, as can be seen in the figure. The annual demand for cement in India is predicted to rise, as can be seen from the figure on the screen. Limestone is the main raw material used for the manufacture of cement. Thus, the demand for limestone will also increase. It is predicted that with the current trend of consumption, the reserves of limestone may be exhausted by 2028 in the high demand case and by 2031 in the low demand case. India meets most of its material requirements domestically. An increase in domestic resource extraction is likely to happen with the increase in projected demand. This in turn will lead to depletion of natural reserves and an increase in carbon emissions from the construction industry. The map of mineral reserves in India is shown on the screen. And this is the map of forests in India. If we superimpose the forest map on the mineral map, we will find that the country's mineral reserves are located under forests. Some mineral reserves are found in the watersheds of its rivers. Years of mining in environments that were rich in flora and fauna have led to large-scale destruction of forests, displacement of millions of indigenous people, and loss of livelihood of many others. Since mining is an energy-intensive activity, it also conflicts with India's National Action Plan on Climate Change. India is the second largest emitter of CO2 due to cement production in the world, as seen in the figure. India has committed to reduce its carbon intensity by 33 to 35% by 2030. The increase in material demand will have a negative impact on the environment, including ecosystem damage, increase in pollution, and irreversible climate change due to the release of greenhouse gases. With so much construction yet to happen, there is an urgent need to replace conventional energy-intensive materials with low-energy alternative building materials, not only in India but around the globe. Alternative materials are those that reduce the demand for virgin materials or natural resources such as timber, topsoil, and river sand, which play a crucial role in balancing the ecosystem. They also meet the need for lowered waste generation. One of the potential ways to do this is by diverting waste from landfill into effective utilization as construction materials. Using fly ash in building envelope with cement is an example of diverting a naturally occurring cementitious byproduct from reaching the landfill, which is otherwise capable of causing all three major forms of pollution, that is air, water, and land. Therefore, The use of low energy alternative materials should be promoted and positively embraced by all stakeholders, including policymakers and building professionals. Alternative materials can be broadly classified into materials from waste, naturally occurring materials, and rapidly renewable materials. The 5 R's principle of waste management has 5 stages that aim at reducing waste generation. To refuse is to deny the use of construction materials that may cause harm to the environment. For example, refusing the use of cement plaster and paint and instead designing for an exposed brick wall finish. To reduce is to use less material by adopting innovative strategies and technologies in construction. For example, use of additives in concrete to reduce water consumption. To reuse is where the product is repeatedly utilized in its original form without any processing. For example, reusing flooring material from an old building in new construction. To repurpose is when a product cannot be reused for its actually intended purpose but can be used for some other useful purpose. For example, use of broken tiles on a roof as a mosaic. To recycle is when a product cannot be reused or repurposed and the product needs to be processed in order to be used again. It involves energy and resource use. For example, use of fly ash in the production of fly ash bricks. Natural stones that are quarried from earth do not contain any harmful chemicals or toxins. If extracted regionally and utilized locally, the environmental impacts of the extraction and manufacturing process can be reduced by limited transportation. Natural stone requires minimum amount of fresh water during extraction and stands the test of time with its durability. Natural stones are considered as green building materials. Similarly, soil-based blocks such as adobe, compressed stabilized earth blocks, wattle and daub, and rammed earth, if extracted and created locally, are considered to be low-impact materials. Rapidly renewable materials are those which have a regeneration rate of 10 years or less, as they are easily replenished. Using such rapidly renewable materials will help meet the growing material demand. They will also reduce the environmental impacts on the regional climate and arrest the deforestation rate to an extent. Materials such as bamboo, cork, straw bale or cotton, wheat board are a few of the rapidly renewable materials commonly used in building construction. For example, bamboo can be considered a good replacement to timber as it grows rapidly and has a high compressive strength compared to wood. The energy used in bamboo production is half the energy used in production of wood. Bamboo has been recognized as a grass by the Government of India and its usage is promoted considering its eco-friendly nature. The use of bamboo in the construction industry can thus help in discouraging deforestation. The construction activity and production of building materials contribute heavily to greenhouse gas concentration in the atmosphere and in turn to global warming. To account for the sum total impact of all GHG emissions attributed to a material during its life cycle, one must consider its embodied energy. Embodied energy is the sum of the energy required to produce any material, considered as if that energy was incorporated or embodied in the product itself. It includes the amount of energy consumed by that material during the various activities throughout its entire life cycle. The energy used for raw material extraction, transport, manufacture, assembly, installation, disassembly, deconstruction, or decomposition, as well as the human energy and other secondary resources are accounted for. Since a building's embodied energy is majorly based on material consumption, the use of low embodied energy materials will reduce life cycle carbon dioxide emissions and eventually the global warming potential of the built environment. The table here gives the classification of building materials based on energy intensity. Energy intensity is the embodied energy value per unit mass. Life Cycle Assessment or LCA was introduced in 1960s for effective management and utilization of materials in various industries. International standards for LCA were laid down in 1997. Life cycle assessment is a technique for assessing the environmental aspects associated with a product over its life cycle. This technique is used to analyze the contribution of the life cycle stages to the overall environmental load, usually with the aim to prioritize improvements on products or processes. It is also used for comparison between products. In the case of a building, LCA helps to understand, consider, and reduce the environmental impacts of the project by encouraging the selection of products with a lower environmental impact, including embodied carbon over the life cycle of the building. For ease of analysis, the building's life cycle is divided into 4 stages, which are material production, construction, use and maintenance, and end of life, as seen in the figure on the screen. LCA can be carried out for various parameters like global warming potential, depletion potential of the stratospheric ozone layer, acidification potential of land and water, eutrophication potential, formation potential of tropospheric ozone photochemical oxidants, abiotic resource depletion potential for elements and fossil fuel. Among all these parameters, GWP, that is global warming potential, has been chosen as the indicator for comparison of GRIHA registered project with GRIHA benchmark. It is among the most popular measure of project performance as it aligns best with the international efforts of cutting down GHG emissions. This is a typical life cycle assessment process. As can be seen, at every stage there is some input, either in the form of energy or in the form of material. And at every stage there is some wastage that is produced. At the same time, there are some emissions to air or water. Many a times, a byproduct is also formed at the production stage. A life cycle assessment consists of 4 steps. First is definition of goal and scope. Second is inventory analysis. Third is impact assessment. And finally, the interpretation. As can be seen in the picture, these steps depend upon each other. In the first step of LCA, we define what exactly we want to analyze and how deep we want to go with the analysis. Defining our goal and scope serves 3 very important functions. First, what we will be assessing. Second, what system we will be assessing in. And third, what we will not be assessing. The second step is the inventory analysis. This looks at the environmental inputs and outputs of a product or a service. It is essentially the data collection phase of the LCA. This means we measure everything that flows in and out of the system. The inputs can be in the form of raw materials, various forms of energy, and resources like water. Outputs would be the product, byproducts, waste, and emissions to air, land, or water. In step 3, we evaluate how significant the impacts are. We select the impact category. Various categories are human toxicity, global warming potential, ecotoxicity, acidification, and eutrophication. For example, global warming potential is measured in CO2 equivalents. This doesn't mean that only CO2 is contributing to global warming. Methane and nitrous oxide also play a role. But to be able to consolidate all gases into one indicator, all other gases are transposed into CO2 equivalents. Finally, we calculate all our equivalents and sum them up in overall impact category totals. And the last step is the interpretation or the conclusion of all the results. There are softwares and tools available for life cycle assessment. The boundary variants of LCA are cradle to grave, cradle to gate, cradle to cradle, gate to gate, and well to wheel. The first phase, being resource extraction, is called cradle, and the last phase, being disposal, is called the grave. Cradle to grave is the full life cycle assessment from resource extraction till the disposal stage. Cradle to gate is an assessment of a partial product life cycle from resource extraction up to the factory gate. The use phase and the disposal phase of the product are omitted in this case. Cradle to cradle assessment is done when end of life step of the product is a recycling process. The life cycle assessment has been explained here with the help of an example of fly ash brick. The life cycle phases are shown here, right from raw material extraction to production, transportation, then use, and finally disposal and recycling. The results of the assessment are shown in the form of carbon footprint and embodied energy. Finally, the environmental impact potential is presented in a tabular form where all the environmental parameters are examined for all the stages. The interpretation of LCA can be presented graphically. The Ministry of Environment, Forest and Climate Change has issued policies to incentivize or deter the use of different construction materials in India. To prevent air, water and land pollution caused by industrial manufacturing processes, the government introduced policies to promote the use of industrial byproducts such as fly ash and ground granulated blast furnace slag, that is GGBS. The policies related to fly ash are: within a radius of 300 km from coal or lignite-based thermal power plants, the manufacturers of bricks, blocks or tiles would use at least 25% of fly ash in their product. It is mandatory for cement industries within a radius of 300 km of a thermal power plant to use fly ash for manufacture of cement as per the specifications of the BIS. Every construction agency engaged in construction of roads within a radius of 300 km from a coal or lignite-based thermal power plant would be bound to use fly ash in accordance with the guidelines or specifications issued by the IRC. It is compulsory for power plants to give fly ash free of cost to users within 300 km radius. Every construction agency engaged in the construction of buildings within a radius of 300 km of TPP has to use 100% fly ash based bricks or blocks in their construction project. It is appropriate to mention here that any brick or block containing more than 25% fly ash is designated as fly ash brick or block. The fly ash brick industry falls under the category of white industries, which will not require environmental clearance. Ground granulated blast furnace slag (GGBS) is an industrial byproduct of an iron blast furnace. The use of this slag along with ordinary Portland cement in concrete is recommended. To reduce waste generation and accumulation, policies have been launched to promote the use of recyclable construction and demolition materials, recyclable plastic, and other waste material in construction activities. There are initiatives like incentives would be given for using materials made out of construction and demolition waste in the construction activity. Recycled aggregates would be permitted up to 25% in plain concrete, 20% in reinforced concrete of M25 or lower grade, and up to 100% in lean concretes of grade less than M15. The Ministry of Railways has formulated guidelines for the use of waste plastic in roads and highway constructions. According to NBC Part 11, the recyclable wastes permitted in construction are rice husk, fly ash, ground slag, crushed recycled concrete, waste stone pieces, bagasse, cotton stock, coir fiber, sisal fiber, and wood residues. Also, metals with recyclable content, salvaged sections, and scrap steels are preferred. Certain policies by the Government of India promote the use of alternative or low carbon or naturally occurring or rapidly renewable materials. Directives are made regarding the use of bamboo, natural stones, and earth-based materials like rammed earth, CSEB blocks, cob, or adobe. Bureau of Indian Standards has formulated codes to dictate the process of material manufacture and use. As we have learned from this video, an ideal sustainable building material is not only environment friendly, causes no adverse impact on health of occupants, is readily available, can be reclaimed, can be recycled, and is made from renewable raw materials, but also uses predominantly renewable energy in extraction, production, transportation, fixing, and ultimate disposal. Practically, this kind of ideal material may not be available. Hence, when selecting sustainable materials, it may be best to choose materials which fulfill most of these criteria. For viewing more such educational videos, subscribe to my YouTube channel.